Okay, hopefully 7.5 should be a short one. We're only doing one section today because you have a quiz over 7.1 to 7.4 at the same time. So we're only going to talk about one thing, independent events. And by the way, while I'm talking about chapter planning here, 7.6 is the last one we're doing. So yes, that's how we're going to get a test in before spring break. All right, independent events. We're going to be talking about how to combine when you combine calculations for probabilities. Like you calculate one probability of one event happening and then somehow adding or multiplying or doing something fancy with another probability you calculate in the same situation, and how to appropriately combine those things. The first way to sort of decipher all that is you have to think about whether or not your events are independent or dependent. I don't know why this section is called independent events, because you notice they define independent and they define dependent, so it's kind of like, I don't know, maybe we should call it event dependency. It sounds like something we need to contact counselors about. Okay, so first of all, what are independent events? Um, well, the biggest one they always come back to is the one about socks in a drawer, like, and whether or not you put the sock back before you start drawing another sock, which is, I can't think of anything more boring than socks in a drawer. But if we're talking about with replacement, then drawing one sock and then putting it back and drawing another sock, choosing a sock from the drawer, putting it back, choosing another sock. The first sock has nothing to do with what you pick for the second sock. Another example of independent events is when you're flipping a coin. You flip a coin once, you think about, you record whatever it was, you flip it again. It has nothing to do with what happened the first time. I've got a funny video reference here of a story where there's a couple of guys on a trip, and they keep flipping this coin, and it keeps coming up heads, and they debate the philosophical nature of that happening in the cosmos and probability. It's really funny. If you're a fan of Shakespeare, you'll really like it. It's sort of a spoof on a Shakespeare. Um, no characters from Shakespeare. Right? You might want to see that. It's pretty funny, and it's from a movie. It's a full-length movie, and this is just the opening scene. Okay, so yeah, independent events. I mean, it's a good name for that. Independent events are events that have absolutely nothing to do with each other, when the first outcome has nothing to do with the second outcome. Okay, here I talk about the socks. There we go. Yeah. And there's a question here. We'll get to this actually as soon as I show you the fact that there is some discussion down in here in the notes about dependent events. But I think from even what I've just said and what we've talked about with the socks, you might have enough to go on right now. We could start talking about independent events and whether or not this little list here, you can classify each one of these as dependent or independent. All right, so if you draw a card from a deck, if you choose a card from a deck, and you keep it in your hand, and then you take a second card, the question is, I mean, are those two things independent events? Is the first card you draw, once you take a card out of that deck, is the second card somehow affected by that? Well, actually, yes, it is. If you pull out the Ace of Spades, then there's no way that the second card could be the Ace of Spades. If you pull out the Ace of Spades, then every card now in the deck for the second draw, there's 51 possibilities. Here's one way to write that, actually. I have 52 possibilities for the first thing, and then that's followed by, and we talked about this last time, that's followed by 51 possibilities for the next time. Not only is there a different number, but they're actually different. Whatever card is picked here has come out of the pool now for the second card, and that's an effect. That's a situation where this event is now depending on what happens here. Okay, drawing a card from a deck, putting it back, and then taking the second card. Well, then, yeah, that's... Hold on, I should write this up here. This first situation was dependent. Part B here. If you put the card back, it's like socks in the drawer, right? So you put the card back in, you have an equal chance of picking it again. The second draw of the cards has absolutely nothing to do with the first one. These are actually independent. And again, pretty soon here we're going to get to the so what about independent. Once you know events are dependent or independent, that's going to help us know how to calculate with them in a second here. Okay, spinning a spinner twice in a row. We're talking about those things where you have, there's a a game spinner or something, you have a little arrow thing that you spin around in a circle, and it lands in one of the colors in it, or one of the numbers in the areas here. If you spin that thing once, record whatever you have, and you spin it again, turns out that the second time you spin it has nothing to do with the first spin. So this is also independent. Should I just write I or D? This is going to take forever. And I have to think about how I spell it. All right, so we're going to start saying D and I now. Back to the little answer key here. All right, and part D, picking the same lottery ticket 2 weeks in a row. Well, what I mean by that is, those lotteries in the States where you go into wherever you get lottery tickets, and you pick 6 numbers that you think are going to come up in the lottery. If you do that 1 week, and whether or not you win or lose, say you go back the next week and you pick the same one again, does the second week's numbers that are going to come up, do those have anything to do with the first week? Turns out that no, they don't. If you have a certain number that comes up in week 1, that has nothing to do with what's going to come in week 2. It doesn't take it out of the pool, so to speak. Picking 2 different lottery tickets during the same week, picking one number at the same time, if you're going to buy 2 tickets, you get to pick another string of usually 6 numbers, and that's, they have the numbered balls that they draw out of a hat, basically. The fact that you picked some numbers on your first ticket has nothing to do with the likelihood that those numbers are going to come up. So by picking a second set of numbers, nothing to do with the first set. Your chances of winning on either one are unrelated to each other. Okay, I try to make up some situations here that get you thinking, and they're not, I'm trying to make them very real life, to get you thinking that probability does come up a lot in real life, and some things that people think are probability, or think that probabilities are very simple, are really, really not. Okay, but sometimes they are. Sometimes they're simpler than they seem. So I'm just trying to give you more examples here. A through H, that's pretty good. Pick 2 marbles from a bag without replacement. All right, this is starting to look, F and G here look a lot like A and B. If you don't replace it, if you take the red marble out, say if you have a bunch of marbles in the bag, they're all different colors, you take a red one out, then you go back to pick a second one. That red one you took out is now disturbing the balance of the original bag. It's not available for the second choice. So the second draw is related to the first one. Depending on what you pull out the first time, that one is no longer available. The bag is a different bag now when you go to make the second choice. So I hope that's clear. But if you do put it back, then they have really nothing to do with each other. Yeah, you could argue that maybe on a fate or sort of astrological level, but really there's nothing that says that just because the first one's red, if you put it back, you've got the same original bag of marbles again to pick from, so they're actually not related. All right, and in part H, this is really complicated. The probability that the first person you ask to go to the prom with you says yes, versus the probability that the second person you ask to go to the prom with you says yes. This is one of those things where people think maybe this has a lot to do with simple probability, but this situation is so complicated. I think I don't even know how to answer that, but I wanted to discuss it a little bit. If you believe, there's so many variables at play here. If you believe that your chances are completely random with the 2 people, then and the 2 people don't talk to each other, and sort of your chances with any of them are kind of the same, then I guess you'd want to say that those things are independent. But usually in the course of high school social structure, once you ask one person, then maybe the way you ask the second person, you might not be as confident if the first person says no. Of course, if the first person says yes, social rules generally have it that if the first person says yes, you shouldn't even ask the second person. So this whole question's kind of moot. There would be no second person. So that kind of tends me to think it's probably somehow dependent. Also, sometimes you ask one person, and then that person says no, but then they talk to everybody, spread these rumors about who you asked, and then that changes everything. So my point is, this is a really complicated situation. I tend to think that, yes, it would be dependent, but you could really make an argument for just about anything. This is not a simple probability situation. So we're going to say, not sure, and we'll chalk it up to high school drama. Okay, so why do we care about independent events? Well, if the events are independent, the cool part about that, or the helpful part about that, is that you can then multiply um, the two probabilities. If you can find each one of those probabilities separately and you're sure that they're independent, then you can go ahead and multiply the two. Dependent events aren't as easy to do that with. So it's good to be able to sort out when you have independent events, because then you can just go ahead and multiply those. All is not lost. If you have dependent events, you can still figure out probabilities there. Usually what's happening in dependent events, when you have to compute subsequent probabilities for multiple events, like say you're drawing one card and then you have to draw a second card. Usually what happens there is, in a situation like that, like the without replacement situations, is that the denominator of each following event usually starts to go down. Like say you want the probability that you draw two diamonds in a row from a deck or something like that. If you're going to draw one card and then you draw another card, that's the probability that you get. Oh, I shouldn't say it that way. I should probably say diamond followed by diamond. The probability that the first thing is going to be a diamond, we've got 13 out of 52 that the first one's going to be a diamond. But then the second probability, assuming that you got a diamond on the first one, first of all, there's only 51 cards left after you pick a first card out. And if you've taken a diamond out, then there's only really 12 diamonds left. So you see how this fraction is completely different from this one. But you can still compute with that. It's just not as clean. You got to think about everything changing as you go in a dependent event situation. In the book, they have an example about socks, and I think they do this wrong. They say that the second sock has a 2 out of 6 chance. I really think it ought to be 2 out of 5, because you've taken a sock out, and they have a chart even, and I think their calculation doesn't agree with the picture in the chart. So I just wanted to mention that to you. Okay, the next thing they talk about in the book is about how they relate mutually exclusivity to independence and dependence of events, and it's kind of thick to try to read through this here and try to figure out what they mean. But basically, the conclusion here is that independent events cannot be mutually exclusive, or you can't have events that are both independent and mutually exclusive. If you think about that, independent events have nothing to do with each other. Mutually exclusive events kind of do have to do with each other in that you can't be both. So there is, they're kind of, that kind of implies some sort of dependence, that they have to not overlap at all. So one does kind of affect the other. It's kind of like choosing teams. Once you choose one team, that affects who can be on the other team. So that's kind of nice, because if we're saying we can multiply probabilities, remember, for independent events, if they are mutually exclusive, then this is supposed to be 0, right? The probability that they intersect is supposed to be 0, which would mean one of these has to be 0, which is a problem if you're talking about mutually exclusive events. You wouldn't want either one of these to be 0, or you wouldn't want to require that one of these be 0 before you multiply them when they're independent. Okay, I've got 2 minutes to answer these questions, or really to get you to the place where you can answer these questions. All right, so if you've got a drawer with 3 red socks and 2 blue socks, what's the probability that you draw 2 red socks with replacement? Well, remember, that means you're going to draw one and put it back. 3 red socks, 2 blue socks. What's the probability that the first sock is red? Well, there's 3 reds out of 5 total. You put that back, start over. What's the probability that the second sock is red? Well, it's the same. So there you go. You've got 9 out of 25 chance that you're going to pull out a red and then a red. If you don't put it back, the first sock, yeah, it's still 3 out of 5. But now, if you've got a red sock in your hand, there's only 4 socks in the drawer, and only 2 of them are red. That changes everything. So this is actually going to be 3 out of 10. Okay. Which above examples of independent events? Well, if you listen to how I said that, basically, this red sock had nothing to do with this red sock. This red sock, look how different this is from 3/5. These were the same. These were different. Independent events was part A. What's the probability that you get all 3 true-false questions wrong on a test if you guess? Well, there's a right answer and there's a wrong answer for each one of those. Probability that the first question is wrong is, well, 1/2. Probability that the second question is wrong has nothing to do with the first question, right? And same for the third. So that should be 1/8. Pretty optimistic there. You only have a 1 out of 8 chance of getting them all wrong. Same thing for this, and I've got about 20 seconds, so I'm just going to... Actually, I'll leave that for you. Multiple choice questions. There's going to be 3 questions, so we're going to be multiplying 3 fractions. what's the chances that you get one wrong? And then you do the, and I would assume those should be independent. Okay, see you in class.